Okay, so we now come to the start of the EDA response again, this time from Luc Bergen of Eve. When we first started this, Luc was part of Eve and obviously now part of Synopsys. Also when we started, Springsoft was a sponsor and now is part of Synopsys. So fortunately the finance departments didn't get together, so we got free sponsorship still. But I know Eve is going to, Luc is going to talk about a bit about being with Synopsys as well. So I'll hand over. What's this? You need a pocket?
Okay. Hello, everybody. Okay, so as Mike mentioned, we had a small event in the company 1 month ago since Synopsys acquired Eve. So I was expecting to make this presentation as the CEO of Eve, but today I will do it as a Vice President of Engineering for Synopsys. That's okay. So at Eve, we had a pretty, we've been pretty successful actually. So we started 12 years ago, starting by doing some services. And then we have been entering into the emulation market, very different way than the other providers. So typically the other providers tend to develop an emulation system and try to make it faster. And we did exactly the opposite. So what we did was more to develop a FPGA kind of prototyping solution very fast, and then add all the features so that it looks like an emulator. And so what we believe we've been able to build in the end is what we call a fast emulator. So it looks a bit like an oxymoron, but we believe now it's really true. Anyway, the company has been growing pretty fast. So just before the acquisition, we were 140 people, and all those people are going to be a part of the Synopsys family now. The company was really profitable. And we had about 60 customers doing all kind of chips, so processors, graphics, SoC. A lot of business actually with people doing modems and application processor for tablets and smartphone. But I guess it should be true for a lot of EDA companies. So differentiators we have been really providing two interesting things, focusing on the standard FPGAs instead of developing our own chips like our competitors. So that's one way to address the two major issues with emulation we have been seeing forever, which are really cost and performance. So by using standard FPGAs, then you have a better chance to address those two issues. And the second thing was to focus a lot on transaction-based verification and how to stimulate a design in an emulator using transactors, how to debug a design using transactors. So that's going to be, that was the focus of the company almost since day one. And these two differentiators will explain why the company has been pretty successful. So today we sell two products. So ZeBu Server, which is a kind of high-end emulation platform supporting up to 50 users. So basically, you might have up to 50 users sharing the machine, or you might have just one user taking the entire capacity of the machine. And it's scalable in the sense that you can go up to 1 billion ASIC gates. And here I'm talking about design compiler gates. I'm not talking about FPGA gates. So what matters, I guess, for you. ZeBu Blade 2 is more a kind of desktop machine, and actually there is a demo system in the room next door. Based on the latest production, the latest chips coming from Xilinx in production, so the Virtex 6. And obviously we are working on the next generation, Virtex 7. So what is interesting with this kind of machine is that we are putting a lot of emphasis on the hardware, because again, this is the right way to address the cost/performance equation. But we are also developing a lot of software, and we have a pretty big team now, about 80 people developing all the software on top of this solution. to make sure that, well, you will get all the debugging feature like if you were using a simulator. So we have been talking today about UPF, about how to manage power. So we have this kind of things about assertion, SVA, and so on and so forth. So a little bit of history on regarding emulation. So emulation really started at the end of the 80s. So Xilinx, which was really one of the first FPGA providers, puts the first FPGA on the market in 84. And a couple of years later, people started to think, well, you know, if you put together a couple of FPGAs, then maybe you can use a board with a couple of FPGAs to implement an ASIC. And that could be a great way to validate a design. Then the next question was, okay, that's great, but now how am I going to stimulate my design? So what is going to be realistic? And the easiest way was really to say, well, you know, it's simple. You take the target system, which is the board on which you are supposed to receive your design, and you connect the target system via cables and so on to the emulator. Okay, so that's the name in-circuit emulation, where it's coming from. Then that was an interesting way to do the things. The only issue is that with the evolution of interfaces, protocol standard, and so on, what we have seen is that it was more and more difficult actually to hook up a system real time. Also, you need to understand that basically when you build an emulator, if you have a lot of FPGAs, then you cannot really provide the same level of performance than the final chip. The final chip is going to run at 1 gigahertz, and the FPGA implementation is going to be more in the 10 megahertz. Okay, so there is a gap here, and you need to be able to implement typically slow down bridges so that you can accommodate the speed of the design in the emulator. And it can be very painful, and especially when you have to deal with protocols like USB, PCI Express, DDR, and so on. So then a few years later, people started to think, well, you know, it would be good if there is a way to synthesize, to make the tester bench synthesizable, to embed the tester bench into the box. Then there is no communication with the outside world. There is no issue regarding speed and so on. It's very controllable. And a typical example is you have a DDR memory. Instead of using an actual DDR memory chip, well, you just create a synthesizable memory model, which is based on a very simple SRAM. And the beauty of the thing is that now you can, for example, pickpoke the memory, you can stop the emulation clocks in the middle of the run and so on. So that's great. The only issue is that it's pretty difficult to write a synthesizable tester bench because given the complexity of the design and the tester bench, you end up spending more time writing the tester bench than the design itself. Then people started to see some value in trying to connect simulation to emulation. So the idea was really to say, well, you know, I wrote this tester bench for my simulation. I would like to reuse it exactly the same for emulation, which is a great idea. The only issue is that simulation is not really fast, which means that if your tester bench is about 10% of the activity for the overall environment, then best case you will get a 10x speed up. And what's the point to spend, you know, maybe $1 million on the box to get a 10x speed up? And then, on the other hand, people realized that it was great to have again this software control, to have a way to stop the things, to do the thing exactly like if you are using a simulator. Keep memories, generating waveforms, implementing assertion, and so on. And so in the middle of the 2000, actually, people really started to put in production what we call transaction-based co-emulation. And the idea here is really to create a software model which is to some extent equivalent to the target system, but make sure that unlike simulation and tester bench, this environment is going to be fast. And the trick is to use transactors. So a transactor, it's not a new thing. It has been used in the 90s by all the networking industry. And a network transactor is basically it's a way to go from a transaction level down to a bit cycle level. Okay, it's very and you can use it for a lot of different things. You can use it for stimulation. You can use it for debugging. We have seen implementation from the team today. And so, yeah, so the trick actually with emulators was, okay, it's great to use transactors, but if in the end the transactor runs in simulation, there is no benefit, right? So the trick was to make it synthesizable. At least what is the most expensive in terms of execution time would be synthesizable. That would be basically all the, what typically we call BFM. So BFM would be synthesizable and would end up being implemented in the emulator. Okay? And so what we see today actually, so it's, I mean, it looks like a serial story here, but what happens today is that people are mixing things. Okay, if you look at the typical SoC design verification today, you will have a bit of in-circuit emulation because you need to hook up a software debugger, and you're going to do that through a JTAG connection. Okay, you will need a bit of synthesizable tester bench because you have again a DDR memory. It's better to use a synthesizable memory model. And then, most of the interfaces like video, Ethernet, USB will be managed with transactors. So the question now is, okay, what is going to be the next step? What are we going to see in the next couple of years? So I asked our marketing folks to send me some data, and so they came back with those slides from the ITRS, International Technology Roadmap for Semiconductors. So first slide is about the complexity of designs, complexity in terms of billion AZ gates, and depending on the technology node. And so what we see today is, so here we are on the 20 nano process. What we see is that the largest processors are basically in a range of 1 billion ASIC gates for the biggest graphics, the high-end graphics chips. And if we look at consumer portable, so consumer portable would be typically application processor for a tablet or smartphone. We are already talking about 150 million gates. So it's very amazing to see the complexity of those designs. Second point, data point, is about processors. So here we have, for portable devices, the requirements in terms of performance. And given that today, obviously, it's very difficult to increase the speed of the device, the only choice is to increase the number of processors. And so you end up with a prediction, which is here in blue, regarding the number of processors. Within 12 years, we expect the number of processors to be multiplied by 10. So if you look at a typical application processor today, like OMAP 5, for example, so you have between 5 and 10 processors on this application processor. So we can expect to have the same type of, for this type of design, to have between 50 and 100 processors within 12 years. And so obviously, if you have a lot of processors, it means that you will have a lot of software, a lot of hardware-software integration challenges. So it's going to be a lot of fun. And that's a bit redundant here. It's about, consumer stationary design. So that would be typically set-top box chips. And the prediction is more or less the same. We're talking about 75 processors within 12 years. Another data point is about power consumption, which is really growing fast. So here we're not obviously talking about portable devices, but we are talking about stationary devices. I mean, now what we see, and that was emphasized by François in the previous presentation, is that power is really a key item in terms of functional verification. It's not just a matter of looking at the hardware, looking at the software, but as you know, you have a lot of connection, let's say. In the past, people, they were just using gate clocks, okay, in the clock tree to reduce the power. And that was not easy to manage for an emulation provider. It took a while, but now everybody knows how to do that. Then people started to use UPF, CPF for power aware, to do all the switching on, off. And it's not, it's not easy to implement, obviously, on an emulator, but people are able to do that. And that's something we support today in our product line, ZeBu. Forgot to mention, by the way, that ZeBu stands for zero bug. And what else? And also power estimation. I mean, that's also a key topic. And we need several things, like power estimation at the chip at the IP block level, but also at the chip level. And as you know, it can be pretty intensive in terms of computing. Anyway, if we summarize, what we see is that the complexity of design is skyrocketing. Number of processors is growing, which means more software, more hardware-software integration challenges. So basically, when you are providing emulation system, you really need to provide something which is going to scale in terms of size. So we need to deal with the complexity of the future design. We need also to provide more throughput, because when you have more software, then you also need more cycles. If you look at the number of cycles you need to boot Linux, it's 10 times less than Android. And Android is 10 times or maybe 100 times less than Windows 8. Okay, and we know that tomorrow we'll have Windows 8, whether, I mean, you like it or not, we'll have Windows 8 on our smartphone. I mean, that's unavoidable. And the third point, which is a critical point, obviously, is obviously the cost. So we need to manage the cost. And when you look at those three first points, I mean, the key thing here is really to have a very fast technology refresh, which really means that today emulation has to evolve. Our solutions today are based on 40 nanometer. Tomorrow we move to 28 and so on and so forth. And we need to go as fast as you, because if we're not able to go as fast as you, then we will have an issue here in terms of capacity, in terms of cost, in terms of performance. And actually, if we are able to run a little bit faster than you, that would be better. Now the other challenges are more related to the debug, the stimulation, how to make sure that well, people are able to stimulate the design in the most comfortable way, make sure that the way we stimulate the design is very close to the actual chip, because it doesn't make sense to stimulate it in a different way, right? It has to be very similar. We don't have maybe the luxury to do a random type of stimulation, so we have to do something which is very close. And how to make sure that the stimulation is going to be very close to the target system, if you will. Also, we need to find a very good way to debug, because today, when you think about a 1 billion gate design, you have like, I mean, it's easy, you know, to generate 100 million bits per cycle, and to make runs like 1 billion cycles. So think about the number of terabytes we need, and what waveform tool is going to manage this type of, I mean, it's, and so we need to find ways and provide ways to raise the level of abstraction for debugging. And so that's, again, what we have seen before with Joachim. And given that here we are dealing with potentially very big design with a lot of different protocols, and obviously no one is, you know, I mean, can know all the protocols, USB, PCI Express, Ethernet, I mean, processor cores, memories, and so on. And last point is about power. I'm going to skip this one because I know it's lunchtime and you are, like me, hungry. So today, what we see in the industry is that people are really moving from RTL to ESL. So it's the trend, even though people are complaining that it's not fast enough. So the move from gate to RTL was very fast, and we are struggling a bit to go from RTL to ESL. But anyway, we see more and more virtual platforms. We see more and more people using C to generate codes, RTL code, and less people writing RTL actually. So that's a good thing. In terms of verification, we need to do the same. I mean, we need to have ways to raise the level of abstraction for the test benches, and also for the way we debug the design. We need to have system-level test benches. We need to have ways to debug the design at the system level. So today, this is a typical environment when you are debugging a design. So you have a software view, you have a hardware view. Ideally, I mean, well, in the end, it's very likely you will use waveforms to debug the design. But what is very important, and again, given the length of the test sequences we're talking about, it's very important to raise the level of abstraction here, to have ways to view the transactions, the frames, the packets, to use protocol analyzer and so on and so forth, so that you can really understand what is going on at the system level, understand why it's not working as expected, and then really focus on the window of debugging and just generate the waveform for this block, for this amount of cycles. So an interesting thing we are seeing these days is that people are connecting virtual platform to emulation more and more. So this is one example. So you have an SoC here, which is implemented in the emulator. And let's suppose this SoC is including one of several Cortex A9 processors. Well, actually, you could use a fast model from ARM, and you run it on the host PC. You hook up, the review debugger, for example, and then between this fast model and the RTL running emulation, you have an XI or several XI transactors, so that you have the communication which is maintained between the SoC and all the peripherals and the processor on the host PC. And then for each interface, well, you will typically need some transactors again, so one interface could be HDMI display, and well, again, we're talking about chip-level debugging. So ideally, what you want is to get, well, the image, the video, be able to do, zoom in, zoom out functions, and so on. So that's one example. We have seen sort of, well, user, customer implementing, for example, a graphics IP in an emulator, and then stimulating this graphics IP with a virtual platform, which is, again, running on the host PC. And in the end, well, it's clear that most of our customers, what they need is also to make sure that the full chip is working fine, right? And today this is the main usage for emulation. Maybe 90% is really full chip design. So then we move the ARM Cortex, we use the RTL, but we still use transactors actually for the software. So we use the ARM vStream transactor, so that there is a way to hook up the review debugger through a transactor, and there is no need actually to use a JTAG connection with cables, so it's much more controllable. And so this is the conclusion slide. So again, what is very important for us is to help the customer create an environment which is going to be very close to the actual target system with the final production chip. And obviously this environment has to be controllable, has to be debuggable. In terms of capacity, we need to scale, and ideally faster than the technology roadmap you are using on the chips, so that we can provide always more performance at a lower cost. In terms of debugging, two things. So there is the story about raising the level of abstraction, but also the fact that we need to provide ways to help to create deterministic and repeatable environments. So in-circuit emulation was not also very deterministic in nature, because you don't sometimes really control all the hardware. But even on transactors, that's something we see, and we need to work on it. Provide a way to make sure that if you do multiple emulation run, you will get exactly the same results. And we have some techniques to do this type of things. And at last, it will be mandatory, I think, for the next generation emulation solution to deal with power. So in terms of really make sure that the power is not going to break the functionality, and also gives you some means to do power estimation at the high level. so that you can find again the hotspot when you are running your design, and then focus on more on using some accurate ways to calculate the power. And that's it. I will be happy to take your question.
Do we have any questions from the audience? So, I know it's lunchtime, but it would be nice to have one or two.
One rather short question. You showed the increasing complexity of your designs. You didn't show the increasing complexity of the test benches. And I also had a feeling that you attack the increasing complexity of the test benches more by going a higher abstraction level. Is this observation correct?
Well, it's true that for most applications, if the complexity of the design is growing, it's very likely the complexity of the test bench is going to grow, and maybe even faster actually, because you will need. On the other hand, I mean, here we are not talking about block level verification, IP verification, right? We are more at the chip level, and so at the chip level, the complexity is how do you model the external environment? How do you model the? So to some extent, you could think, I mean, for example, on a laptop, we are integrating everything. Now on the processor, you have everything. So it looks that the target system is simpler. But you need to deal with many interfaces. Before it was just you as a processor, an interface with the North Bridge, okay, maybe one bus. And now basically you need to deal with PCI Express, USB, SATA, and so on, and you get an SoC. Now if you look at the next generation processor, they are going to be SoCs. They are not going to be processor anymore, right? And so it's a bit different. But I mean, it's clear that if there is more complexity in your design, it's very likely you will have more complexity in your test bench. Except that in the end, again, what we're trying to do here is to model the target system. And we are trying to create all the possible ways of stimulating the design, which is even more complex, right? I'm sure if you go from maybe 1 million gate IP to 10 million gate IP, maybe if you want to do all the kind of randomization, it's going to be at 100x complexity, maybe 1000x complexity. When you are dealing at the chip level, I think it's, well, fortunately a little bit more simple.
And there was just one question online again, which was how much of the power verification that Francois described could be done for the ZeBu box?
Well, we need to be reasonable, right? I mean, obviously you cannot do everything. I mean, a simulator is by definition much more flexible, and you can do a lot of things. But I mean, what is nice today with emulation is that you can manage, for example, UPF. You can implement synthesizable assertions. So you can basically have, in terms of interaction with the tool, an environment which is quite similar to a simulator. And obviously now, for us within Synopsys, the goal is really to create a smooth experience for the user to go from VCS to ZeBu. So we are going to have a bit of work, I believe, but that's really the goal. And the vision for us is really to create an environment where it's easy to move from simulation to emulation.
Okay, thank you very much. Luc?